at the Third International Congress on Access for Dialysis in Maastricht, Holland in 1997. Physiology and technology behind excess recirculation and excess flow measurements by ultrasound dilution technique. As you know, excess recirculation always measured a normal line position, and if dilution techniques is used, in this case, we inject indicator into the venous line. So what's happened? Indicator can have two choices to travel. One of them through the vascular access back to arterial line. It's where excess recirculation takes place. Another way, and it always happened, the indicator coming through the venous line, through the right heart, left heart, lungs, and come back into the arterial line. So what we see here, it's always a competition between these two guys. And the main purpose of recirculation measurement to find out what to actually measure here, recirculation or cardiopulmonary recirculation, named CPR. So if there is recirculation, the traveling distance is very small. It's only 6 to 15 ml per minute to travel this recirculation. But if the indicator travels through the CPR, it takes near 1 liter. The volume is here 1 liter. So the distance or the volume that indicator would travel here 1,000 times less than here. But the speed of traveling also different. If there is recirculation, it can travel in average 100 ml per minute, like speed, right? And the cardiac output, that actually the speed, how the indicators travel through the cardiopulmonary system, maybe, let's say, 10 liters. So they different again in 1,000 times. So if you want to know the time is always the ratio of the volume of for traveling on the speed. And this ratio, this to this, and the ratio of this to this is pretty the same. So actually, there's a real competition between these two guys. So if you want to find out who actually, the first one, it's very important in the beginning, in the venous line, to record the time when this traveling starts. So when the injection was made, right? And then, after some time, after, for example, 5 seconds, the hemodialysis monitor records that something is coming to the arterial line and finish. We actually don't know this time who is this guy, recirculation or cardiopulmonary recirculation. We don't know. We only know that something is coming to arterial line. So to understand, to find out who actually coming there, we developed a huge archive of more than 10,000 curves that were recorded by different machines, a different type of tubing, for different vascular access, and for different type of injections. And this archive give us opportunity to find out what actually we measure at the arterial line. And we find out that if patients have recirculation, this is actually a significant recirculation. In this case, the traveling time of the indicator to the vascular axis is small. It's from 2 to 6 seconds. But if the traveling time is more, it may be both. It may be small excess circulation, or it may be very quick cardiopulmonary circulation. If this axis is in upper arm fistula and the cardiac output is high, the time that takes indicator to travel through cardiopulmonary system also very small. So in this situation, we really need to make a decision what we actually see, recirculation or CPR. This is how this technology was developed. And of course, in majority of the patient, the time that takes for indicator to travel through the heart, through the lung, take from 8 to 20 seconds. In this case, it's simpler to separate real recirculation from cardiopulmonary circulation. So actually, the question that we need to answer is there a recirculation or no? And the thousands of measurements that were done by this technology show that majority of the patients have no excess recirculation. But within 5 5–7% of the patients have vascular excess circulation. And all these patients have a compromised vascular access, significant stenosis there, and in both native fistulas or artificial graft. So if there is a circulation, it's always a problem with the vascular access. Vascular access is measured at reverse line position. So to measure shunt flow, we reverse hemodialysis lines. Why we don't need this thing? When we reverse the line, now we withdraw blood from the venous part of the vascular access and return it back to arterial line. This is a venous outflow. Why we do this? We create artificial circulation loop. Now the outflow of the venous line is mixed with the inflow of the vascular access, creating mixing conditions. It's a fundamental requirement on all the dilution technologies. As soon as we met this requirement, we can measure shunt flow here, right? So when we make an indicator, it's mixed here, coming through the vascular access, and is withdrawn part of it by arterial line. But as before, another part of the indicator will travel through the cardiopulmonary system and come back here. And as you see here, the time of the traveling is pretty quick. So what's happened, if the artificially created circulation here still going on, and this second part of the indicator coming during this time, for example, this injection is too long, for example. In this situation, what can happen? That CPR, that cardiopulmonary circulation, will jump on the artificially created real excess circulation and compromise our measurement. We will not know what we measure. For this, and the error may be huge, 40%. For this purpose, this hemodialysis monitor will make a special, develop a special way to separate these two events to protect our measurements from the influence of cardiopulmonary circulation. So what we actually find out, great majority of the vascular access have a flow from 800 to 1800 ml per minute, and there is actually no significant stenosis in this vascular access. It's actually related both mostly to the artificial grafts and also to native fistulas. If the flow, for example, in artificial grafts are in the order 600, 800 ml, and if you even see the trend coming from this to this, we already expect stenosis in this vascular access. But if we see the flow of in the order of 600 ml per minute, for sure there is significant stenosis in this vascular access, and this access is in potential danger to clot pretty soon. Of course, we find out that some patients, mostly native fistula, the excess flow may be huge, 2 to 4 liters. Unfortunately, in this situation, the heart may be overloaded, and this patient is in a potential danger. And we are seeing in many situations, doctor make a compromised decision and, for example, bundle this vascular access to decrease the flow to save this patient. So what we can do here when the patient is going to clot pretty soon? And this is actually the main idea of this technology. It's a trend. It's measuring the excess flow, let's say initially, maybe as soon as you put this vascular access, or at least later, and then follow up it in time. And if we see that the vascular access starts going down, we should do something here, because for sure this patient will clot. So at least now we see in publication that early intervention in this stage can save this vascular access for a longer time. And again, I think this is the main point of this technology, monitoring the vascular access flow and make intervention in right time. In this case, we can prolong increase the capacity of the vascular access. And of course, this great movie was produced by and directed by Nikolai Krivitski, and illustrated and inspired by Raisa Krivitski, and assisted by Pavel and Lucy Krivitski. I'm sorry, Ludmila Krivitski. And this is the end of the story.